start recording session 2 and share my application screen. But before, let me delete everything that I have from the previous session. I think I can start a new one. Yes, that doesn't matter. Okay, so as I was telling you, well, telling some of you who were here earlier, I kind of fixed the problem with the tablet, but I had to change computer, so now I'm going to be using EndNote. I still don't know how to save my notes after I'm done with the session, but I will figure it out. But at least now I can write on the tablet, okay? So tonight we're going to discuss live tables. And live tables are really important tools that actually is used to estimate probabilities, to estimate insurance benefits, and a lot of things. So far, we have been working with functions, and you're probably still working with functions in the problems and everything. And those functions are really useful, but what we are going to do is, well, it's really complicated to have a function with you all the time and provide that information to an individual. For instance, if somebody wants to estimate specific probabilities, and you just tell them, okay, yes, you can do that by assuming that this individual follows this mortality law and these blah blah the parameters. If you have a computer, and again, nowadays it's easier because now we have laptops and we can do these things really, really fast. But just think about 10 years ago or 15 years ago, we didn't have, well, there were laptops around, but it wasn't that common to have one with you all the time. So what we did, we used live tables, and that's still something that we do. Live tables are a way to summarize mortality experience for a population based on specific parameters. And we're going to learn how to estimate live tables tonight with using Gompers and Mayhem perspectives. But again, this approach holds for any mortality law that you want to use, okay? So let's start with basic definitions. Okay. So as I was telling you, live tables are really useful to follow mortality or survival of specific populations. And what we do is we usually take specific lives. So we take, I don't know, 100,000 individuals, 1 million individuals, and that number actually is not really that important. But we're going to assume that we have one population starting at one specific age. In general terms, this age is x0, and usually x0 equals 0. So essentially, we can start our live table at age 0. But sometimes we can start our live tables at age 12, 15, 65, or some other different age. So not all the time the starting age is going to be 0, but chances are we will be using that most of the semester. This age, or essentially the population that we have, the number of people that we have at age x0 is what we call the radix. And essentially, this is the original population that we have. And this is the population that we are going to follow until the extinction of the last survivor. Okay. Now, essentially what we are going to do is for any age x that is greater than x0, so essentially if we start at 0, we are going to estimate this for 1, 2, 3, 4, 5, and so on. Or if we start at 15, it will be for 16, 17, 18, and all other ages. We are going to estimate the expected number of survivors, or we're going to list the number of survivors. And then based on that, we're going to be able to estimate probabilities and to estimate people dying in our population and so many things. So using actuarial notation, what we have is x is the age x of our population, and lx, this is the number of survivors at age x. So this is important because sometimes, and you will see at the end of this session, sometimes when we are given a life table, we are just given this column. Essentially, we just have that information. Again, this is the number of people surviving at this specific age. And with that, we need to estimate, or we should be able to estimate any probability that we want. And it's easier than probably that it sounds, but again, we need to discuss little by little these things. So again, assuming that x0 equals 0, essentially what we will have is we can estimate this number of survivors at age x, taking our radix, and this is the number of life at age x0. So essentially, this is L0. This is what we call radix. So we take our original population, and then we take that population times the probability of surviving to a specific age x. Or if we have some other perspective, we can estimate, if we didn't start at age 0, but it doesn't matter, we can estimate the probability of the survivors at age x plus t as our original population times the probability of this individual surviving t years. Again, from this expression, it's really easy to see that we can, if we have the list of survivors, and this is what I was telling you right now, sometimes you just get this column as the input information that we have, and we can estimate the probabilities. Why? Because from here, I can estimate the probability, or I can see the probability of surviving t years is essentially the survivors that I have at age x plus t divided by the survivors that I had at age x. And this is more like essentially a frequentist approach of probability. Just think about casos favorables, casos totales, and that is what we have here. And if we are starting at age 0, what we have is this. So a lot of these things, again, this is actuarial notation. I think, I don't remember if it was in this section on the one on Tuesdays and Thursdays, but somebody was telling me, I know the answer, but I still don't know how to express it with actuarial notation. That's fine. These are things that we're going to be using a lot, and you will get used to this notation. And by the end of the semester, you should be able to look at any of these things and say, okay, this is the meaning of these symbols, okay? Go to the next one. This is what I just did in the previous slide. Essentially, in general, we can estimate the probability of surviving from age x to age x plus t as the ratio between survivors at specific ages, okay? So now we have, let's see that we are building our life table. And a life table is gonna look like a table. First we have x, then we will have TPX. And here we can have 0, 1, 2, and this would be, well, any value that we have here. Then we have LX, survivors. And sometimes, because this is important, we want to estimate the number of people dying. Yes. So this is the expected number of deaths, or the number of deaths that we have in our population between ages x and x plus t, where t again can be 1. So if it's 1, I just don't use that notation. It's something that we won't be using. But it's really easy to see that the number of people dying is nothing but the difference between those that I have alive at age x, and then subtracting those that are still alive at age x plus 1, and the difference will be, of course, those who died in this interval. This is a 1-year interval, but again, I can have an interval of length t, and again, it's the same formula. And from here, I can also see that this essentially is Lx subtracting Lx times Px, which is this. And from here, I get this, which is the one expression that I have here, which is a different way or another way to estimate those who are dying. Essentially, the number of people that are dying in this 1 year interval is those that I still have alive at that age times the probability of dying between that age and the following one. Okay? Sorry, I wasn't paying attention to the chat, but I think everything is fine. Okay. And down here, I have the same, but instead of having 1 year interval, I have t. And again, is the same process if I want to move from one to the other one. Which again, if I have survivors, I can have people dying. If I have people dying, I can estimate the probability of death just by realizing that this Qx is those who are dying divided by the survivors that I have. Again, if I just clear this expression from here. And again, this is something that we're going to be using a lot. We're going to be moving or like changing expressions and replacing expressions in order to estimate things that we need to estimate. Okay? So this is the way, again, a life table looks. This is just a fragment of a life table. Here we have age X. We have survivors at that age, which is the LX. And we have those who are dying between age X and X plus T, or in this scenario, T is 1. So you can see this dx is the difference between this. And again, if I wanted to continue my life table, it's really easy to get the following number by just taking 18 out of 40, and this would be 22, right? Yes. And then that's the last thing that I can estimate because I don't know the number of people dying. But again, I don't know if I actually don't need that right now. Okay. So with this life table, let's estimate this probability. This is the probability that a person age 71 survives to age 74. And just remember the general expression for this. This is Lx plus T, Lx, which in this scenario would be age 74. So that would be the survivors at age 74. It's a really ugly 4. Divided by survivors at age 71, which in this scenario is really easy to estimate. So this is the probability. Just like that. So these things are really or relatively easy, but I can get creative, and this is what I usually do with the problems that you need to solve for, even for the activities or for the exams. So here, this is a different example. Now we have some information in a life table. With this information, we want to estimate the probability of a newborn surviving to age 2. Essentially, that is the meaning of this probability, okay? What would you do to estimate this? Any ideas? No? Okay, let's start with what we have, or ideally what the things that we would need in order to estimate this probability. Remember that, again, this is H0, but again, the general expression is this. X plus T and X. So this translates as 0 plus 2, so that would be survivors at H2 divided by survivors at H0, which we don't have. We have this, 890. We don't have this. Okay, so what can we do if we don't have that? Any idea? We have time, right? Okay. So somehow I need to estimate that value, L0, okay? Or my radix in this scenario. So I need to use this information somehow to get to this value, okay? So let's see what we have. We have this, the number of people dying between age X and X plus 1. So let me just move this. So essentially, the number of people dying at age 0, which is 50, how would you get this in general, like under any circumstances, ignoring that we don't have, that essentially ignoring the fact that we have missing information? It's right here. So the number of people dying is the survivors, and then subtracting survivors the following age. So in this example, essentially this D0 will be L0, which again, we need this. So again, at least we know that we're getting close because we have that value here. And then subtracting L1, which we don't have either. But somehow I need to get to these things. So I have, okay, that's another approach. Yes, L0, okay. D0, L0 times, now P1, no, it will be Q. And again, these two are equivalent at the end of the day, but okay. So let's ignore that. So I know that now, in order to estimate L0, I need L1. So how can I get this value here? What I do know is, well, yes, at the end of the day, it's going to be that, but let's do it step by step. I have this probability. So essentially what I know is that the probability of surviving at age 1, from age 1 to age 2, is going to be survivors at age 2 divided by survivors at age 1. And guess what? Guess what? I have this because this is this 0.98. And I have the value of L2, 890. So I can get the value of L1, right? So this means that L1 is L2 divided by P1, which is 890, 0.98. And how much is this? Okay, 890 divided by 0.98. Okay, thank you, Ana Carla and Jesus. So this is 908.16. I'm just gonna leave it with 16. Now I have L1, and using that I can estimate L0, right? So essentially this means that L0 is 50 times 908.16, meaning this 958.16, which now allows me to, like, for estimation of this thing, because this is gonna be 890 divided by 958.16. And how much is this probability? I can help you with 0 point something. Thank you. 92,886. So again, this is something that you probably will find in the problems that you have to solve. And again, in real life, chances are you're not gonna find things like this. But again, these examples are really useful because they help us, like, to identify all these associations between these columns. And here we only have 3, but see how with 3 columns and 3 values we can estimate this probability. And even we can estimate every probability of a person age 0 surviving to age 1, and then from age 1 surviving to age 2. Well, we already have this. And again, we don't have for next age, but again, so we are not able to continue this life table. So that's the idea of these examples, like to start working on the associations between these variables. Because in reality, we only need 1 column in our life table besides age, and with that column we can estimate all values for our life table, which is really neat and is something really useful. Okay, so questions from this example? Okay, wonderful. So things that are really useful when we're working with life tables. The first thing is that we know that there are some basic associations or things that we always are going to find in life tables. So one of those things is this fact. Always, the probability of dying plus the probability of surviving, well, this is the other way, surviving plus the probability of dying in the same interval, this is important, with the same interval, if we add these two, we will always get, we will always get a 1, because again, here we're talking about mortality and survival, and there is nothing else. It's either you are alive or you are dead, just like that. So this is something that we can use a lot of the times, and we're going to be using this for a lot of examples and problems in the future. Now, something else. Remember that omega is the limit in age, or the last age that we have in our population. We use these values of omega when we're working with the Moab's mortality law, but we're going to find that here in life tables. In life tables that we're going to be using here for actuarial mathematics, we usually are going to be fine, or we're going to be okay just increasing the value of omega. We can go for omegas of 110, 120 years, 140 years, that's fine. We can model that. When we're in demography, for those of you who are in demography, we're just going to be really, really practical assigning this value. But again, the idea of this limiting age is that since we know this is the last age, then the probability of dying at that age has to be 1. And that is something that we're going to do sometimes in life tables. If we know that the last age in our population is 90, we're just going to go and input 1 at age 90, and essentially we're killing everybody. And since we're killing everybody, essentially what we have is that at that age, the survivors that we have are going to be equal to the people that are dying in at that age. And again, that makes sense because we're killing all the survivors since the probability of death is 1. Okay? So this is what I was telling you. We only need information in one column, essentially, or one function, and we can develop a life table. And that's what we are going to do in probably 4 or 5 minutes, okay, to create our life table. Okay, so we can use information, as I was telling you. If somebody gives you the information on survivors in a table, and that is something that I will send you probably tonight or tomorrow, more likely. Again, you can recreate a life table, or we can use some mortality law that we know. Again, we can go with Gompers, we can go with Mayhem, and essentially the examples that we're gonna do tonight are what Mayhem and Gompers. Just remember that this is force of mortality for Gompers, and for Mayhem, the only difference that we have is that we have this additional factor of A. This is Mayhem. So the survival function, or in this scenario, the probability of surviving from age x to age x plus t, is just e to the negative value of the interval between these things of the force of mortality. And I don't think we solve this step by step, but again, this is the complete solution for Gompers, and again, for Mayhem, you can just recreate this thing. But at the end of the day, we end up with this expression. And again, don't forget that in actuarial terms, this is the expression that we have, or in actuarial notation, which again is nothing crazy. We're just gonna do it right now using Excel. Of course, if I do it, if I ask you, build a life table using your calculator, pen and pencil, or pencil and paper, you're gonna hate me if I ask you to do that by hand. But we're going to use Excel spreadsheets, so it shouldn't be a problem. And again, this is starting at any age x. As I was saying, we can start at age 12, 15, 65, whatever. But if we start at age 0, essentially this thing gets even easier, because that means that c to the power of 0 is 1, and then we just replace the value of t with x, and we will end up with this expression, which is, again, a simplified version of this thing that we have right now, right? Sorry, the Gompers general expression. So we just need values for the parameters b and c, and from there we can work and create our life table. So, for instance, and this is the way these life tables look. These are 2 parameters, and we can play with these parameters if we have time later. Again, I have to give you B and C, or at least, as we did a couple of sessions ago, or last session, I don't remember, or at least giving you 2 values for mu x, and then you will be able to estimate the value of these parameters B and C. Chances are I will give you the values of B and C because again, it's just practical. And we can estimate the survival probabilities. And again, if we start at H0, this is what I was telling you happens. If we start at H0, this becomes 1. And we have a simplified version of Gompers, and we can build our life table for any value of t, which in this scenario becomes x. But we can start at H20, at H50, at H80, and again, it's just replacing the value of our H here, and then everything else is going to be the same, which, as you can see, essentially we're just multiplying by a factor. So we are moving the function in, if we have a graph, and we will see one graph right now, we're just moving this function to the right or to the left. So this is the way that looks. So if we build this life table, and this is the survival probability, or SXT, and this is T, of course. The first thing that we see is that all these expressions meet the criteria for survival functions, right? In 0, they're all 1. When we have large values of t, they go to 0, and these are non-increasing functions. So if we have our life table starting at H0, this value of t represents essentially the age at death of these individuals. So we see that first we have really like little mortality, and then around age 60 we have an increased mortality, or like people dying at a faster pace. So that's the reason the survival function goes down, and then it kind of has this really nice shape at the end. So what happens if we start at age 20? Now these values of t is the future lifetime of these individuals at age 20. So essentially, this would mean that this 20 is age 40, right? So these are the survivors at age 40 and age 50, 60, and so on. And as you can see, it's the same shape essentially, but we are starting later in this plot, and then something happens, something similar happens when we start at 50, and when we start at 80, essentially, people has to die, and mortality is closer to our original age. But again, this is the same Gompers function. Again, just changing the starting value for our life table. Okay. And again, let's use the approach starting with x0, essentially our starting age being 0. So we're going to estimate this thing, which in our example is going to be the probability of surviving to age x, or this using a trial notation. Okay. So essentially what we will have here is the survivors at age x are going to be the consequence of two things. First, the original value that we are going to use, and this is something that we just are going to tell, okay, this is 100,000, 1 million, 10 million, whatever. And these probabilities that are going to come from Gompers or from Mayhem, or any other function that we have. But right tonight we're going to be working with Gompers. Essentially, let's build it for Mayhem, and then Gompers is just a, it takes the value of 0, and then it's a Gompers function. So it's here, this is the same expression that I have here. And then once we estimate survivors at age x, we can estimate probabilities for every single age x, and then people dying, and then the probability of death. So something important is, and this is where sometimes people get confused with these things. The first thing that we are going to estimate based on Gompers and Mayhem is going to be this, or starting a different age, we will be estimating this, which is not the same as, as this, because this one is from age 0 all the way to age x. So it's going to be from age 0 to age 5, from age 0 to age 23, from age 0 to age 47, whatever. Or if we were using a different age, this would be from age 15 to for 5 years, so that would be from 15 to 20, or from 15 for 10 years, that would be from 15 to 25, and so on. This probability, remember that this has a 1 here. So essentially, once we have these and survivors, we are going to estimate for every single age X the probability of a person dying at that age. So essentially, for only 1 year, which is not the same as the previous probabilities that we get from Gompers and Mayhem. Okay? So, in order to do that, open an Excel spreadsheet. Let me share my complete screen, or my entire screen, so you can, no. Entire screen, share. And I'm just gonna start with a new one. Okay. Okay, so let's start with Mayhem. And then when we work with Gompers, essentially that would mean that A is 0, okay? So again, I have to give you the values or the parameters that we're gonna use for Mayhem. So let's make A 0.000, 3 zeros, and then 1. Where did I get this value? I got them from the book that I use for the class. The Dixon is on the references for on Blackboard. So that they use these values a lot, so that's the reason I just decided to go with these values. Then for B, it will be 0.00035. Again, 3 zeros and then 35. And for C, let's use 0.075. No, sorry, 1.075. Okay. Okay, now this is the expression for, well, the parameters for a Mayhem model. So let me go back to this. I think I can use, I think I have actually, yes. Okay. So the first thing that we need to do is to have a column for values of X. So that's gonna be really easy. And then we are going to estimate this thing, which based on the things that we had before, will be E to the negative value of AT plus B, the natural log of C, and C to T. Okay. This is the expression that we're going to use to estimate these first probabilities. Since we have B divided by the log of C here, and I want to avoid having lots of parentheses in my formula, I am just going to estimate that here as a new element in Excel, which I'm just going to call M just because I don't know why. It's going to be B divided by the natural log of C. So I don't have to input that every single time. Now, let's start with values of X, 0, 1, 2, 3. And just let's estimate all the way to 120. I think, yes, something like this. Okay, are you there with me? Because the next step is the one when these things get kind of tricky. Okay, so most of you, I think you're there with me. Okay, so now let's estimate the probabilities of these people age 0 reaching age X. Let me just make this look nice. I want this to look nice. Okay. Okay. So according to my formula, is x the exponential negative a times t. But look, realize that it's something important. A, B, and C are not moving for every hx. So essentially, well, this is, sorry, I wrote t, but again, because we're starting at h0, this is the same as having this. Okay. So is a times x. So one way to ask Excel to leave that value as a fixed value, so essentially not moving the cell, is just using $sign for that thing. So that's the way this is not going to move. So it's a times x. Then I have b divided by the log of c, which I already estimated here. And again, I'm going to use $sign times c to the power of x plus 1, then 1, 2, 3. Okay. What is the value that I should get in this first cell? So what is the probability of a person H0 surviving to H0? 1. And yes, I got a 1. So this is nice because at least I know that the first one is correct. Now, but this is a really nice way to double check that everything is working. So that is a nice thing. And since I was careful of leaving these values like fixed with the $sign here, the only thing that is going to be changing is the BA. So when I copy and paste this to the next cell, it's going to be B9 and then B10, 11, and so on. I can copy and paste this formula or just double click. And I have all these probabilities. Yes, 120 was a lot. I could have stopped at 110, but again, I just decided to go all the way to 120. So what you get here, let's just double check if this is a survival function. And yes, it is, of course. So, okay, let me change this thing. So with value in 0 equals 1, for large values of t goes down to 0, and is a non-increasing function, which again is the 3 criteria that we need to do these things. So let me just again, you don't need to save this, but I will do it just because I want to have it here. I think let me. Okay, So I just want to have a survival function there. And we will come back to this. Again, you don't have to do this, it's just me like having that in there. Okay, so now we have the probabilities of surviving from hx all the way to, sorry, from h0 all the way to hx. Now, according to the things that we need to do, now we need to estimate Lx, which is going to be these probabilities, sorry, times L0. So first we need to define the value that we're going to use for our L0. So is this value of L0 is, again, there's no written rule. We can use any value, but L0 is usually 10 to any power. So we can even use 1 if we want to, but again, that is more for like mathematical demography and actuaries working on mathematical models. So let's just use 100,000. And now, in order to estimate the value for X, I'm just gonna multiply this 100,000 times the probability of surviving. Which is this times this. And we can pull the formula. And I'm just gonna hide the decimals because, again, these are people. I know the decimals are there, but I don't want to see those. I don't want to see them, just hiding them, okay? And something that is gonna happen, or probably you already noticed, is that this column, Lx, sorry, this is Lx, not L0, is nothing but this survival function times 100,000. So this is just the same, it should have the same shape that survival function has, but instead of starting in 1, we're going to start in 100,000, but it's the same, okay? Now, let's estimate the probability of survival for every single age. So that I have just copy and paste. Which we already know how to get, because it's for only 1 year interval. So this is going to be for every single value of hx, it's going to be Lx plus 1 divided by Lx, just like that. How do we get the probability of dying? Yes, just like that. Just the difference between essentially one minus the probability of surviving. Because again, that's a rule that always happens. And of course, as the probability of surviving starts going down, the probability of dying starts going up. And then at the end, well, here we just ended up with a 1 because, again, we didn't have any additional years. And that's something nice because we always know that in this scenario, 120 is our omega. And what else are we missing? Let me write that. So this is 2x, px, and we're just missing the number of people dying. And we can get this as the difference between Lx and LX plus 1, or we can get that as LX times QX. These two are equivalent because, again, yeah, I did it before, right? I can break these. I don't know if I did it in this class or the other one, sorry. So from here, I can split this as LX times, sorry, go through PX, which translates into LX1 PX, which is LX times QX. So these two are equivalent expressions, okay? So let's just use the second one because it's the direct one. So LX times X. And again, here we can also hide the decimals because I just don't like them. Something interesting is, since I highlighted all these columns right now, look at the sum of everybody who's dying, and of course, everybody who's dying is the 100,000 that I have here at the beginning. So again, everybody has to die eventually. So this is something really nice. Okay, questions here? No. Okay, what if I ask you, okay, no, we don't have a Mayhem model, we have a Gompers model. That's fine. This is a Gompers model. Just taking the value of A as 0. Okay, but let's see what happens with these things. See what happens when I increase the value of A. What happens to my survival function? Again, this is still a survival function. Okay, it's not changing that much, but what is happening, you can see, is declining like faster at the beginning. So it's not moving. My last age or the value of omega is kind of not moving. And I did that. It's just essentially like I'm killing people earlier in life. Now let's see what happens if I change the value of B. Let's double the value of B. Here, what is happening, I am moving the value of my omega. So it's moving to younger ages. Even though the mortality is not happening here, it's more essentially affecting the end of my distribution. So again, you could tell, or you could say that A is affecting more at the beginning of life and B is affecting more at the end of life. But the two of them, what are doing is essentially affecting the way my population dies. So now go back. And C is a really complicated parameter because look what happens when I just change it to 1. It goes crazy because we have issues with the log of 1. So it cannot be 1. With 1.5, look what happens. Essentially, I'm just killing everybody before age 20 or 25, which again, it would be really, really interesting to see in what conditions I have that, or 0, 1. What happens when I just change it to 1.01? So this parameter actually changes a lot. So just be careful because, and it makes sense that it's changing a lot because this is the parameter that is associated with age. So yeah, that happens. Okay, so no questions on how to build a life table? Okay, now that we have our life table, we can solve or we can answer some basic questions. Okay, so let's just ask two really, really straightforward questions about mortality. First, let's estimate the probability that a person who's age 65 survives to age 85. And then let's estimate the probability that a person who is age 35 to survive to age 65 and then dying before age 75. How would you estimate these two? And we have 15 minutes, so we have time. So this is probability that a person age 65 survives to age 85. And this is the probability that a person age 35 survives to age 65 and dies within the following 10 years. So any ideas on either one of these two? Okay, Andrea. Yes, exactly. So the first one is actually what we have been doing already. So the probability of a person age 65 surviving to age 85 is just survivors at age 85 divided by survivors at age 65. And we have these two values from our table. So I'm just gonna go here and so 65 and 85. Well, some is 85 by 65. So I'm not gonna write all the values, so just this. Just using our live table. Okay. So, thank you, Andy. The next one, it's a little bit more complicated, but we did something like this in last week. Wait, Cirilo, I'm almost done. Thank you, Lupita. Exactly. So this deferred probability of death or probability of dying is just the difference between these two probabilities of survival. Essentially, is the probability of a person age 35 surviving all the way to age 65, then subtracting the probability of this person age 35 surviving to age 75, which is going to be, let me Now we can use the previous expression, right? Or a similar expression as before. So this is gonna be L65 divided by L35, and then L75 divided by L35, which we can simplify as this. And now we have a live table. Nothing is stopping us to estimate these things. So let's go here. And this is going to be 65 and then subtracting 75 and then divided by 35. 0.2688. So these questions on these examples? Okay, so you can solve some additional problems from the problems that you have online. There are probably a couple of life expectancies that you can probably solve, but it would be interesting to see what you do with those things. Actually, you can solve those things. Because now, for instance, remember that we discussed last week life expectancy. So now if I give you a life table and I ask you to estimate this life expectancy, you know that you're gonna start adding these things, right? And if you have a life table, you have these values and you can just add them. Of course, here it says it goes from t being 1 to infinity, but infinity in our scenario would be 120 for the example that we had before. So this is a really nice this is an interesting thing. Using the life table that we just estimated, let's see what is the value of this is the quartile life expectancy, right? Not the complete, but the quartile, because we have a discrete scenario. So according to this expression, this would be, we have to add from 1 all the way to infinity, these things. This is something that we can do. Let me delete this. Essentially, this is asking us to add all these values starting here all the way to infinity, but our infinity is 120. And we get a quartile life expectancy of 66.38. And how much would be the complete life expectancy? Come on. So remember that this equals this. Okay. So now this is not only the life expectancy, but complete life expectancy or the quartile life expectancy. This is again the first moment of our random variable, which is really nice. At least I think it is. So something that you probably, if you start working on the problems for this week, you're gonna see, or you're gonna find a couple of problems that actually ask you to use the illustrative life table. So what is that? That is a life table that I will send you. but it's essentially this. Okay, let me just illustrative life table. So if I just type illustrative life table, the first thing that I'm going to find is the SOA website. And here they have these tables are the same. So it's just one is hosted in the other one. So let me just click on the first one. So the first thing that you will find, because we are actuaries and these things are things that we know how to do, is a normal distribution table. Why? Because sometimes, and we will see that when we discuss premiums, there's a way that we can estimate premiums assuming a normal distribution and so things. So you actually have to use this table if you ever take the exam for insurance. Well, it's actually multiple life contingencies. That's the name of the exam. That's the reason it says MLC. And then here comes what is known as the illustrative life table. This is the life table that actuaries use. They start with LX of 10 million, but again, we started with 100,000. We can just replicate this table with these values. So they start with 0, 5, 10, 15, and 20 because it's not really common to have policyholders really at young ages, but then they start going one by one. And then instead of giving us the probability of death, they are giving us the survival probabilities. They're giving us the probability of dying, but just using a factor of 1,000, so we can have values that are really, really significant. And then all these things that are things that we are going to learn how to estimate, and these are things that we're going to use this semester. So again, you can just Google for it, and you can download this table. I will send you this table on Excel. I didn't copy all the table. Essentially, I just find out what was the parameters that they were using for this table, and then I just replicated the table on Excel. So I will send you this table if you want to work on the problems, and a problem is asking you to use the illustrative life table. Essentially, this is the one that you have to use. Okay? So, questions? Ooh, I like this thing in the window. Okay. No? Okay, if there are no questions, let me see how far we. I think we're doing. This is a good progress that we have. Yes, we have. Yes, to estimate the mean life expectancy, variance for life expectancy. This is nice. Oh, fractional ages. That's a really nice topic. Next session is fractional ages, and then select mortality. I don't like that. Okay, so if there are no questions, see you on Wednesday. Have a good night.